Okay, good afternoon, everyone, whoever is joining us from Uzbekistan. Today, we're very happy to host Professor Rustam Ibragimov, who is one of the top scholars from Uzbekistan and working abroad. Professor Rustam Ibragimov is a professor of finance and econometrics at Imperial College London, and he's also a Ph.D. he received his Ph.D. in economics from Yale University. He also did a Ph.D. in mathematics from Uzbek Academy of Sciences. Besides, he's worked as associate professor of economics at Harvard University from 2005 to 2012, and he was a visiting scholar at Cambridge, Oxford, and Columbia universities, and many other universities as well. His key research areas are financial crisis and market contagion, and robust econometric and statistical methods, risk dependence modeling in economics and finance. Today, Professor Ibragimov will be talking about new robust inferences in economics and finance, implications for market efficiency, forecasting, and econometric analysis. Rustam, welcome to our Research Talk series webinar. We're very delighted to host you.
Thank you very much, Ikboljon, for great introduction. It's great to be here. Many thanks for the opportunity to present our research. Great to see our colleagues, friends, teachers, and students here at the seminar. I look forward to April in 2 weeks, our lectures at Tashkent State University of Economics. Our alma mater, in some sense, will start, and it would be great to meet in person and discuss research in person as well. This talk, colleagues, is on new robust inference in economics and finance. I will focus on several important problems and topics in finance and economics, including implications from robust inference for market efficiency analysis, forecasting, and econometrics, economics and finance in general. Here, the talk will focus on several new results in this direction that we just recently obtained with our colleagues. And also, I will touch upon several other applications of the methods, including those we worked on with Jenny Hao, Si-Yun He, Ji-Hyun Kim, Christian Parlor, Rasmus Pedersen, Anton Skrobotov, and John Walden. And I hope we will also be able to discuss, we will have time, several open research topics, and it would be great to discuss them further and possibly collaborate on them. Concerning motivation for robust inference in economics and finance, when we look into the dynamics of key variables in these fields, including financial returns, here on this diagram, we see the plot of the time series of returns on Dow Jones Industrial Average over the period that includes Black Monday crisis of October 1987. On a single day during the Black Monday crisis, the Dow Jones Industrial Average experienced the largest downfall in its history. It fell by more than 22%. We recognize that, unfortunately, economic and financial markets are subject to effects of crisis to the effects of outside and structural shocks. Further, when we look into the dynamics on financial returns, we can observe that there are some statistical regularities over different periods. And actually, these regularities are shared by many other securities, but different markets, different time periods. We can observe that the sign of the move in the asset price is unpredictable, impossible to predict whether the market is going to be up or down. Financial returns are uncorrelated over time, we say, in statistics and econometrics. In some sense, they are unpredictable to some extent. Absence of linear autocorrelations means that future return cannot be predicted using linear models, linear regressions. RT regressed on its previous value. And to some extent, markets are efficient. All the statistical properties of financial returns, asset prices, are related to key fundamental questions in finance and economics, including, as we mentioned, the question of whether markets are efficient. Signs of the moves in asset prices are unpredictable. Returns are uncorrelated, but something about the market is predictable. We see that once the behavior of the time series of returns becomes interesting, there is a pattern of high volatility, movements of either up or down of large magnitude. That period of large volatility, high volatility, stays there for some time. In other words, there are periods of volatility clustering. That is, although returns are uncorrelated, they're simple nonlinear functions. Squares are correlated over time, or volatility today can be predicted using its past values. Fundamental questions in finance and economics are whether asset returns, prices, volatility are predictable, whether markets are efficient, and naturally, what can we do about financial markets, their effects and causes. These research topics are very important, as we know. They are fundamental in economics and finance, and naturally, research on properties of financial markets, including statistical properties of financial returns and prices, has led to recognition by Nobel Prizes for researchers. In 2013, as we know, Nobel Prize in Economics was shared by Eugen Fama, Lars Peter Hansen, and Robert Shiller exactly for their empirical econometric analysis of asset prices. Eugen Fama, as we know, is the father of the concept of market efficiency. He proposed to say that markets are efficient if the best prediction of future return given any information available at time t-1 is 0. This is true if we only know the information contained in the past return. Returns are uncorrelated. Robert Shiller, on the other hand, thought about other information, other variables that may be known at time t-1 that may be useful to predict future asset returns and prices. One of these variables that has predictive ability for forecasting future asset returns and prices is dividend over price ratio. If you look into this regression, return regressed on log of dividend over price ratio, the null hypothesis, our focus is on statistical hypothesis, and everything may be formulated in terms of statistical and econometric hypothesis. The statistical hypothesis, coefficient beta-1, slope coefficient equal to 0, is rejected in favor of the alternative according to research by many researchers, including Robert Shiller, John Campbell, and others. The current dividend over price ratio is of help or has predictive power for forecasting future returns and asset prices. Returns are predictable, so it appears that markets are in fact not efficient. And the debate whether markets are efficient or not is still ongoing, as we know, in economics and finance, with the focus on developed markets as well, markets of emerging economies, new markets like crypto and others. Concerning regressions of this type, we see that the data in them, variables, are problematic. Returns are clearly not IID, as we discussed. Squares of returns are correlated over time. Further, naturally, a current dividend price ratio depends on its previous value just because dividends accumulate over time. They are non-stationary. Similarly, asset price, it grows over time, fluctuates over time, so that this variable is non-stationary as well. We cannot use the standard methods that work for under simple assumptions of IIDness, normality of the variables, in the case of essentially any models in economics and finance, any econometric and statistical models in economics and finance that we are estimating, looking at, involve problematic data. Returns are not IID. Dividends accumulate over time, clearly not IID, and similar for asset prices. When we look into any models that involve dependent, problematic variables, heterogeneous variables, variables that have outliers, as here, great downfall of Black Monday crisis, October 1987, the standard approaches cannot be used. Actually, what is important when we have a series that is close to IID, stationary return is stationary, it doesn't fluctuate away from a constant zero. It's mean. When we have stationary time series, a great thing is that still law of large numbers holds, as we know. Also, CLT can be used, but of course, the standard errors of estimates in the case of variables that are correlated over time, they are different from those that we use in the case of IID assumptions. In other words, when we have heterogeneity over time or dependence over time in stationary time series variables, like it's always the case in economics and finance, we need to adjust our standard errors. The IID standard errors, of course, will not work. And we know different modifications of IID standard errors that are suited for different problems. In particular, wide standard errors is for independent but heterogeneous disturbances, errors, where variances change over time. The variety of standard errors, estimates of limiting variances of estimators, when we have both heterogeneity over time plus dependence over time, autocorrelation over time, data is not independent, like in the case of returns or autocorrelation in dividends, asset prices, dividend over price ratio. The most widely used standard errors in the case of the problems of heterogeneity and autocorrelation over time are New West and Andrews standard errors, as we know. They are different types of heteroskedasticity and autocorrelation consistent standard errors. In addition to the ones that I mentioned, White and Horowitz standard errors are used, Davidson and De Jong and others. Standard errors that account for both heterogeneity, autocorrelation over time are widely used in financial econometrics, economics and finance, as we know. They have been used in different works for predictive regressions, including the important paper by Campbell and Thompson, and in the case of new markets, crypto returns by Lewy and Savinsky. Together with authors, we also looked into applications of robust inference alternative robust inference methods that I will focus on. When we have dependence in the case of other type dependence, not over time, but possibly over individuals, we used clustered consistent standard errors. Consistent standard errors that work for panel data for special correlation dependence over space. Especially correlated standard errors are available. The idea is that when we have a lot of data, the standard errors can converge to the true standard deviations of estimators. The idea of the analysis of or developing of standard errors is naturally based on the law of large numbers. We have infinite or very large data, very large samples, then we can trust our standard errors. In theory, they work perfectly. Law of large numbers holds for large t's. Therefore, when we look into the t-statistics of our estimators, like t-statistics in the regression, but divide the estimate not by IID standard error, but by Hack standard error, adjusting for autocorrelation and dependence over time, heterogeneity over time, then we will have convergence to the standard normal distribution and then proceed with the standard analysis as we do in the IID case. Unfortunately, in practice, we naturally have we have finite samples. And in that case, in particular, because data is very problematic in finance and economics, a lot of outliers, pretty much dependence over time. Because of these reasons, unfortunately, the standard approaches in econometrics to inference and autocorrelation over time, heterogeneity over time, do not work well in terms of statistical properties. Suppose that it's about, say, predictive regression. I want to predict certain dependent variable, perhaps economic growth in the future, the rate of economic growth using certain four predictors. Perhaps those may include the standard ones like interest rate spread, the difference between the interest rate on long-term and short-term government bonds, some other predictors. The simulation design may be similar to Andrews that we use, that dependent variable YT may be economic growth is regressed on a constant plus 4 potential predictors. Assume that it is indeed the case. In the case of economic growth, that is autocorrelated over time. Economic growth follows after regression with after regressive coefficient. Let's put it here. Standard estimates are around positive 0.2, as I remember, for the states, but let's consider others, perhaps even pronounced autocorrelation over time. Similarly, regressors, we assume autocorrelated over time, dependent over time. So let's see what happens to testing the hypothesis that certain coefficient at certain regressor here, predictor, say, coefficient at interest rate spread equals to 0. We apply the standard approach. The statistic of that coefficient is calculated, estimate the regression, get the estimate, divide by CAC standard error, say new standard error, or here it's for Andrews optimal standard errors. Let's see what is the percentage of time the true null hypothesis? True null hypothesis is that coefficient equal to 0 whether our approach rejects it. It appears that the true null hypothesis is rejected too often. The predictive regression will incorrectly conclude that a certain regressor is a good predictor for economic growth, although it's not, although in fact the coefficient is 0. We will reject the true null hypothesis more than our goal, 5% times. We consider 5% level test, that is, reject the null if the statistic is greater than 1.96, the 5% critical value of standard normal. Reject if absolute value of the statistic is greater than that threshold. Colleagues, as we usually ask at seminars and lectures to please stop me at any time if there are any questions or if you need to discuss anything in further details. And the standard approaches do not work well when we have dependence over time in Y, dependent variable, and also in regressors. So we need to think about the alternatives to the standard approaches based on consistent standard errors. For some time, we worked with colleagues on the developments of simple to implement alternatives to inference based on consistent standard errors. That is now referred to in the literature as robust statistic approaches. I will describe it and then focus on important application. Inference in predictive regressions for financial returns. We will think whether the markets are efficient or not. There are other applications we worked on with colleagues and co-authors, including the analysis of income inequality, analysis of statistical properties of financial markets, nonlinear dependence, volatility clustering, and others. I will further discuss several directions for potential further applications of the approaches that we currently thinking about. It would be great to discuss them. And concerning simple alternatives to consistent standard errors, imagine that we want to conduct an inference about a certain parameter of a certain time series, say, be it returns. We want to test whether the mean of the returns that are dependent over time equals to 0. Or perhaps we want to test that the rate of economic growth in a particular country is high, say, equals to, say, 3%. Observations may be months, maybe quarterly for economic growth, so daily economic returns. Or we may think about a coefficient in the regression, dependent time series Y regressed on X predictor, and we are testing the hypothesis that beta coefficient in the regression equal to 0. Whatever the problem is, let's divide our data set time series into some fixed number of groups, say 2 groups. Suppose that it's about testing mean equal to 0. Consider time data from 1 to t over 2, half of the sample, and from t over 2 to t capital. Estimate the parameter of interest, say mean, for the first half of the sample, the first group, and the second group. From t over 2 to t capital, we get 2 estimates, mu1 hat, mu2 hat. Those are just sample averages of our observations. Now, in our approaches, those variables, group estimates, are averaged. We consider average of group estimates, and then that average is normalized by a simple standard deviation of this group estimate. Suppose that there are 2 groups, as we mentioned, Q equals to 2. Standard simple variance of these 2 estimates is, of course, mu1 hat minus average, mu1 hat plus mu2 hat over 2 squared plus mu2 hat minus that average squared. So consider the t-statistic, square root of 2 multiplied by average minus whatever we postulate under the null, mean equal to 0 we mentioned, divided by square root of the following expression, sample standard deviation of these two estimates. Then in our approach, we reject the hypothesis that coefficient of interest equal to some value, say mean of returns equal to 0, in favor of the alternative different from 0, if absolute value of this t-statistic, calculated using group estimates, is greater than 1 minus alpha over 2 percentile of student t distribution with q minus 1 degrees of freedom. Q is the number of groups. Q equal to 2, it's 1 degree of freedom. We consider quantiles of Cauchy distribution. We have the results that show that this simple to implement approach, divide and conquer. Just divide data into some number of groups, maybe 2 or perhaps 4 or 8, some fixed number. Estimate the coefficient of interest, perhaps mean, or maybe it's about regression. Y regressed on X for the first group, X1 to X2 over 2, say, or maybe X1 to X2 over 4 for the second group, and so forth. Group Q get Q estimates, and then consider the statistic of these Q variables, beta 1 hat and so forth, beta Q. By the way, they, of course, these group estimates are asymptotically normal because CLT applies under general dependence over time. Essentially, the results that we have show that whenever we have asymptotic normality for group estimates, this holds if asymptotic normality holds for full sample estimator. Samples are sufficiently large, plus group estimators are asymptotically independent, then the t-statistic approach to inference is asymptotically valid. Also, robust confidence intervals may be constructed in the same way as we do in the case of IIDness, but we use quantiles of student t distribution instead of quantiles of standard norm. More generally, the approach is valid when group estimators converge to scale mixtures of normals, or variances here may be random, covering a wide range of heavy-tailed models, say, under heavy-tails infinite variances, convergences to stable distributions, and that is scale mixture of normal. Essentially, our approach provides a formal justification of widely used Farmer-Macbeth method of inference in finance and economics. Asymptotic validity of the approach follows is the following from the following remarkable result. It's due to mathematicians Nail and Gabor Tseke established quite recently in 2005. I believe in few years this result will be in all textbooks in probability and statistics. That result provides analog of student Gosset result in the case of independent normal observations with possibly different variances. Suppose that here we assume that data is problematic, but we have large samples, as in our diagram for research. Suppose that data is perfect. We have small sample of them, as in the case of student problem who considered inference in the case of independent identically distributed normals. More than 100 years ago, the problem is simple. We have some number of observations, maybe 2 or maybe 8 or maybe 10 small samples. Everything is great about data. Data is ideal. uh, observations are independent. Further, we assume they are normals. The only problem is that variances are different. How do we approach the testing hypothesis mean equal to 0 against mean equal different from 0? Well, following a student, we can conclude that it's natural to reject the null when average of our observations is very different from 0. But the question is how large it should be for proper rejection, justified rejection of the null hypothesis. So let's consider normalized ratio. Sample mean divided by sample variance, estimate of the variance of observations, so to speak, square root of this. A student became famous, statistician William Gossett became famous because he derived the density of this ratio, the statistic we call it, in the case of equal variances. We call the corresponding distribution student T distribution now, with skew degrees of freedom. But what should we do in the case of variances are different? Well, let's see. We need to look into the probability that true null hypothesis is rejected. We reject, and it's natural, when this statistic, the same as student used, is greater than some threshold. In other words, when sample mean is very different from 0. Interestingly and importantly, when we take the worst case scenario, consider maximum of this probability of rejecting the true null, type 1 error, overall possible variances. The maximum is achieved in the case of equal variances. It's very difficult proof and a very involved proof, but this holds. And this holds whenever the level of the test is smaller than 5%, equal to 5%, the most commonly used value. Not the case for 10% level test, interestingly. In the case of equal variances, the T statistic has student T distribution Q minus 1 degrees of freedom. So in this analysis with small samples of ideal data, we may use critical values of student T distribution, or the standard T test is applicable even in the case of unequal variances. It further holds under random variances remarkably. When we want to test the hypothesis about location of certain heavy tail distributions, say Cauchy. Cauchy distribution has no mean, but it has the center. A lot of outliers there in our data. It's okay, remarkably, to use the T statistic and reject when T statistic is greater than appropriate critical value of student T distribution. A lot of outliers, whenever we have heterogeneity in data and we look into density of T statistic, the density importantly becomes bimodal. Here I plot the density of T statistic in the case of ideal data, normal equal variances, then we have bell-shaped symmetric student T distribution for T statistic. And here the blue line is the case of problematic our observations with a lot of outliers. Their distribution is Cauchy bimodal. So mass shifts from the tails to the center. And what important to us is that in the tails, when this threshold is large, the tails of student T dominates. This is what this result says. It's okay to use the same critical values as in the case of homogeneous, ideal, normal observations. Now, that was the result for ideal data, small samples, normality, independence. How about problematic data that we always have in finance and economics? Let's go back to our initial problem. We have many problematic returns. There is a dependent over time, or maybe regression of autocorrelated variable y, economic growth on some predictors, interest rate spread, autocorrelation in Y and regressors, what helps us naturally is the fact that now we have large samples. Under large samples and stationary problematic data, we have asymptotic normality. We can be sure that our group estimators, they are asymptotically normal with some limiting variances, but we don't care about limiting variances in statistic approaches. It's valid because of the small sample result. Group estimates are Q normals with possibly different variances. So we apply the small sample result for asymptotically normal group estimates. For the t-statistic, it's about the question that coefficient center of these variables equal to 0, say. Consider the t-statistic calculated using group estimates reject if t-statistic and group estimates is greater than appropriate quantile of student t-distribution with q minus 1 degrees of freedom. Also, the robust confidence intervals may be constructed. The approach is very simple to implement. Divide data into groups, run the regression, say, or estimate model for each group, get Q estimates, consider t-statistic in this Q asymptotically normal variables, group estimates, reject if t-statistic greater than quantiles of student t. Considering finite sample properties, I'm coming back to predictive regression. One problematic autocorrelated variable y regressed on 4 regressors that autocorrelated over time. And the goal is to see what is the percentage of rejections of true null hypothesis. Beta coefficient at one of the regressors equal to 0 when that hypothesis is true. We see that the statistic approach doesn't reject the true null hypothesis. We are close to 5%. Do not over-reject too often. We are close to our goal. Percentage of rejection is close to the level of the test. Further good size properties of testing procedures, robust inference procedures come together with good power properties. One should mention that there were many attempts to improve on consistent standard errors. Say, the approach of Kiefer and Fogelson there, one gives up on consistency of standard errors, but still normalized by them. Convergence is not too normal. Some complicated non-standard distribution, some improvements in size properties, some improvements of power. But we know we applied researchers don't like convergence to non-standard distributions, although quantiles may be simulated. And unfortunately, those approaches have not been used widely in applied research. The statistic approaches are simple. Divide and estimate the model for each group, then look into the t-statistic. So the advantages of the t-statistic approaches are summarized here. Importantly, we do not need creation of new tables. It's all about student t-distributions, any software or any statistical book will give those. We do not need to solve the difficult problem of estimating limiting variances, often difficult to compute consistent standard errors. We have appealing finite sample performance applicable under general conditions. It's all about asymptotic normality of group estimators, but we know it holds because for full samples it holds. Plus asymptotic independence of group estimators. Well, that is restriction on type of dependence, but it's more explicit than in the case of HAG. There, for HAG applicability, we need to assume mixing conditions that are hard to verify. strong assumptions on moments. 8 moments, finite 8 moments is required for applicability of new West standard errors, but we know returns are heavy tail and force moments are typically infinite for developed markets, let alone emerging markets. There was a wide range of different applications of the approaches, including ones in works that we looked at, that we worked on with our students and colleagues, and also by other researchers. One of the recent applications just recently published in 2024 and 2025 is that in the analysis of predictive accuracy of forecast. Timmerman and Zhu used statistical approaches to develop well uh, well-motivated and well-justified test for quality of forecast. So let us focus on applications of the approaches in predictive regressions and forecasting models. It's about returns, say, regressed on some predictive variable, maybe dividend over price ratio. As we discussed in economics and finance, unfortunately, the standard assumptions of IIDness do not hold. In predictive regressions, we typically have problems of persistence over time. Dividend over price ratio is very persistent regressor. Fit after regression, that will be, after regressive coefficient will be close to 1, non-stationarity. We typically have the problem that regressor, the error U in the regression is correlated with the regressor. Endogeneity problem. Stochastic volatility in the errors is observed. So these are well-known stylized facts in predictive regressions in finance and economics. Naturally, they complicate applicability of standard inference. IID standard errors cannot be used. Adjustment need to be made. Say, under endogeneity, we have the problem that T-statistic on OLS estimator will not be asymptotically normal, and then one needs to deal with that problem. Some of the several solutions to the problems have been proposed, including those in Campbell and Yogo, Phillips and Magdalena's. Endogeneity indeed can be resolved using some versions of instrumental variable approach. We will talk about it. Then some applications of IV estimation together with time change in Choi, Jarvis, and Park. Endogeneity is resolved by instrumental variable analysis. We focus on new inference under the problematic predictive regressions. Work on the heterogeneity of the correlation, persistent contingentity, simple to implement based on robust statistical approaches. Let's see. In order to apply the statistical approaches, the idea is to divide into groups, estimate the coefficient in predictive regression for each group, then look into the t-statistic, base inference on that. We need asymptotic normality. Unfortunately, if we have persistence in regressor or potential persistence or endogeneity, then asymptotic normality is lost. So what is interesting though, the modifications of OLS estimators that are asymptotically normal. For instance, if instead of OLS is about we remember, it's some xt times yt divided by some xt squared to power minus 1/2. That instead of OLS estimator that is now not asymptotically normal, let's consider Cauchy estimator. Multiply y variable dependent variable not by x's but their signs, in normalized by sum of absolute values of x's. That estimator is asymptotically normal even if x is persistent. And or more precisely, when we have stochastic volatility in x, the problem of endogeneity, then we will have convergence of numerator to mixture of normals, scale mixture of normals. But for scale mixtures, we know that t-statistic approach can be used. So we can apply t-statistic approach when we estimate, calculate Cauchy estimators for each of the group and then look into the t-statistic. Cauchy estimated the name, interestingly, goes to Cauchy himself. He considered it around 1823, and interestingly, it finds applications in resolving important problems in econometric and statistical analysis. Concerning the statistic approach, it's very simple. We divide our data into some number of groups, calculate the following statistics, numerators of Cauchy estimator for each of the group, and we have the result that group estimators converge to scale mixtures of normals. Robust statistic approach is valid. We can look into t-statistic and group estimates and then reject the null of no predictability if t-statistic is greater than critical value student t. This approach works well in finite samples. We consider different types of potential dependence in y and x variables over time, including dependence that was dealt with in the literature in simulations. This includes geometric Brownian motion, may be natural for financial markets, regime switching models, thinking about outside shocks. Concerning size of the test, t-statistic approach that is very simple to implement has nice, good size properties, close to the target 5%, never exceeding it. Similar to computationally difficult. Yes, there was a question. Any questions, colleagues? And the size properties of t-statistic approaches that are simple to implement are close to or similar to difficult to implement approaches based on Cauchy estimators and random change of time. Also, OLS estimation doesn't work in principle. It over-rejects the true null hypothesis. This in the case of geometric Brownian motion dependence also. We have good finite sample properties, size properties in the case of regime switching models. That comes together with good power properties. There are settings where t-statistic approach is better in terms of power as compared to computationally difficult to implement Cauchy random change of time method. So these approaches are good complements. So this is on theory. The t-statistic approach works well. Also, it may be coupled together with some other approaches, including non-parametric correction of volatility to account for endogeneity and volatility of regressors. Let me present now empirical results. It's about the question whether the markets are efficient. The Nobel Prize question, the one that Nobel laureates Fama, Lars Peter Hansen, and Robert Shiller have focused on, whether there are some variables available at time t-1, some information at t-1 that is useful to predict future asset returns and prices. This question was the focus of much attention in the literature. As we know, there was a seminal paper by Goyle and Welsh that concludes that no predictor exists that can consistently predict the equity premium more accurately than its historical average. This statement was challenged by several works, including Campbell and Thompson, who concluded that if there are sensible, well-motivated restrictions on predictive model, then a good predictive model exists. Good predictive model means that the model is in sample significant, the definitions are due to Goyle and Welsh. The model has good performance out of sample, delivers good forecast. Also, the overall performance of historical average of the model is not poorly caused by oil period, oil crisis period. Also, we have good performance in recent years. Concerning Campbell and Thompson, they considered regressions of asset returns, or more precisely equity premium, corrected for interest free rate on different predictors. Very simple regression that we looked at, focused on the analysis of out of sample performance and sample performance in terms of R square. In our work with Jenny Howe and Alexei Min, we consider application of robust inference methods, divide into groups, estimate predictive model for each group, then look into the t-statistic, and the same predictors as in the case of Campbell and Thompson. Those include dividend price ratio, we mentioned equity premium, earnings to price ratio, other important variables that were tested as potential predictors. Campbell and Thompson argue that if one applies sensible restrictions to regression models, including equilibrium restrictions, consider inflation and growth adjusted, dividend over price ratio, earnings price ratio, plus some sensible restrictions on out-of-sample forecast, then we can obtain a good predictive model, conclude that they exist good predictive model. Campbell and Thompson use HAC estimators in their analysis. So let's see whether that is motivated. They look into monthly regressions involving monthly returns, annual returns. When we look estimate autocorrelations of monthly returns, we see that some of the autocorrelations are different from zero. Many close to zero. Annual returns, a lot of autocorrelations are different from zero for many lags. Good motivation for the use of robust standard errors. And Campbell and Thompson use heteroscedasticity consistent estimator of white with some adjustment for finite samples. We will refer to as W standard errors. Also, for illustrative purposes, consider IID standard errors. Also, motivated by autocorrelation in annual returns, Campbell and Thompson also use HAC, heteroscedasticity autocorrelation consistent standard errors from White and Domowitz. For some reason, they do not use widely used HAC estimator of New West that we typically see in research in financial econometrics. In this paper, we look into performance of all these standard errors, including New West, HAC, and also consider applications of robust statistical approach. So let's see, what can we say about in sample significance? It's actually new as compared to Campbell and Thompson on performance of the predictive regressions. We see that much more potential predictors are in sample significant according to New West standard errors as compared to heterogeneity consistent standard errors that are used in Campbell and Thompson. This is for monthly returns. T-statistic approaches also indicate in sample significance, importantly for valuation ratios like dividend over price ratio. And there inflation and growth adjusted versions, where the adjustment motivated by equilibrium considerations. So the conclusion is that we further provide further support for the conclusions in Campbell and Thompson that valuation ratios are good predictors for returns and asset prices. Interestingly, IID standard errors are not correct, should not be used, of course, but well, the conclusions of robust testing procedures interestingly coincide with conclusions on those. One may think what the reason is that maybe type of autocorrelation. Perhaps instead of accounting only for heterogeneity, the standard errors involving potentially autocorrelated returns, monthly returns should also use autocorrelation adjusted standard errors. I will, if it's okay, I will take 5 more minutes, then conclude, colleagues. Okay. Concerning out-of-sample performance, this is very new. The T-statistic approaches that we described and worked with colleagues have been used in the recent paper by Zhu, Timmerman, and Zhu on comparing forecast accuracy of different predictive models. Suppose that it's about testing whether predictive ability of one model, maybe historical average, is the same as that when we use predictive regression or maybe machine learning model. What are the advantages of machine learning besides standard predictive econometric predictive regression? Well, this is about testing equality of means, and then the standard approach may be based on T-statistic for this hypothesis, equality of means, and the estimate of standard error needs to account for potential autocorrelation. This is the approach in the literature. Going back to standard test of Diebold and Mariano test for equality of predictive ability. Zhu, Timmerman, and Zhu also recognize that in many cases we may be interested whether forecastability is the same in all periods and the same in the future for the models. It's not just the case that one of the models, because of the oil price shock or some structural shock, performs in that period better. For testing this hypothesis, equality of several means, the authors propose to use the statistic approach. Plus, let's focus on applications of this test in the case of predictive models considered in Campbell and Thompson. We consider different types of sensible natural restrictions on forecast, including those on positive slope, positive forecast, that Campbell and Thompson naturally regard as being natural. So it appears that in a number of settings, for a number of variables, including price and growth adjusted smooth earning to price ratio, that variable predictor delivers statistically significant better performance than historical average. It's the column corresponding to New West. Estimate analysis for this hypothesis that performance is good over all out of sample period. For the hypothesis that performance is better in all subgroups of future out of sample period, we look into the statistic approach. Our conclusion is that with this standard natural restrictions, positive intercept, bounded slope for predictive models, positive slope, and forecast, smooth earnings to price ratio and its equilibrium adjusted versions are good predictors. Also, predictive ability is confirmed for the following dividend over price and growth adjusted variable under different restrictions on predictive model. So we join Campbell and Thompson and other researchers in conclusions that stock markets are actually predictable, and valuation ratios such as price to dividend ratio, earnings to price ratio are good predictors, and further research for different markets would be interesting. We have some results for cryptocurrency returns, finding that dividend over price ratio also works there, but there are no dividends for crypto. We need to think about the analog. Emerging markets, including markets of countries of CIS, would be interesting to look at. And these are the summaries of the conclusions for predictive regressions. Concerning conclusion, we now have new robust inference in economics and finance that is simple to implement. In many cases, it has better performance than widely used alternatives based on consistent standard errors. Very simple to implement. Divide and conquer. Divide data into some number of groups, estimate the parameter of interest for each group, then look into the t-statistic in this group estimates. We now work on several further applications of the approaches, and it would be great to discuss them. We would be very happy if our colleagues will join on this project. One of the ideas is that the statistic approach essentially works in any two-stage inference, including instrumental variable regressions, analysis of copula-dependent parameter. For instance, as we know, when we have problematic regression, y regressed on x, and there is an indigeneity problem, x and u are not independent, we use instrumental variable because regression, because otherwise the estimate of beta 1 hat is not consistent even in large samples. Instrument is the one that is correlated with x, but is not correlated with u. Say, in estimation demand, we find the variable that moves only supply but doesn't change demand, and the inference in IV regressions is simple, and it's two-stage. X regressed on Z. Then find the estimates, predict X, and then in the second stage, regress problematic Y, endogenous Y on X. We get consistent estimates, but naturally, it's not OLS standard error of beta 1 hat in the two-stage. In the second stage that we need to use, we need to use IV standard errors. Calculation of them becomes problematic when we have time series and other complications. What is interesting, the statistic approach works. Divide data into groups, get IV estimates for each of the group, look into the t-statistic. Also, several other problems involve two-stage inference, including estimation of copula dependence parameters, like estimation of parameters of dependence functions that join marginal of one-dimensional distributions into joint distributions. So it would be great to discuss these topics and possible research. Thank you very much, colleagues. I hope that I'm roughly in time. I would be grateful for any comments or questions.
Thank you very much, Professor Ibragimov. It was a very interesting presentation and very extensive one. And I think we have many participants who are ready to ask questions. Please, everyone, if you have any questions, feel free to write it in chat, or you can ask directly here.
Yeah, I have some comments. Okay.
Mm-hmm.
Okay. The first thing,
Okay.
in order to build these confidence intervals, you emphasize the student t distribution.
Mhm.
But let's assume the financial markets. So in many cases, we reject the null hypothesis that the skew is equal to zero, meaning that the third moment is not zero, the skew is not zero, meaning that it's the asymmetric type of distribution. But so in your development here, so when you presented, you just these things actually developed based on the T distribution, and T distribution, the skewed it's not skewed distribution, symmetric distribution. Okay, is there any development with regard to the considering the asymmetry in the distributions to build the confidence intervals?
Yeah, thank you very much, Akram. I think I think here it's important to emphasize that we, or again, perhaps think together about the types of data that we have in finance and economics. Naturally, data is problematic. Data in particular is not normal, of course, because there are a lot of outliers. Normal distribution will never give a crisis like that. Minus 22 in simulation from standard normal is not possible. Plus, as we see, Akram has mentioned it, we have asymmetry, like in addition to stylized facts or statistical properties mean equal to zero after correlations are absent, we have the property that the magnitude of large downfalls greatly exceed magnitude of upward moves, right? But so data, distribution of data is problematic, plus structure of the data is problematic. Each observation may be correlated or dependent on the past. But the power of limit theorems, suppose that it's about calculating sample mean or estimating sample mean. Mu hat sample average of x's, we know it's consistent for the true mean and asymptotically normal under a variety of assumptions on initial distributions, like in law of large numbers and CLT for sample mean, convergence to symmetric standard normal, we have only to assume finite variance. This is the case for IID, plus the power of the limit theorems is that even wide ranges, very wide ranges of dependence over time may be assumed, and still in the limit its convergence to the nice normal. Data is problematic, not normal, a lot of dependence, but in the limit we have a great, our favorite, standard normal distribution. So what is important in the applications of the approaches, our data is problematic, but estimates are good in the sense that distribution of group estimates is nice, symmetric normal, and that this helps together with small sample result to deliver simple to use approaches. It's about testing mean equal to zero for a bunch of great normal observations. On the other hand, and thank you, Akram, for pointing this out, it should be the case that in some settings, the distribution of this t-statistic in group estimates is still far from student T. And some adjustment like considering maybe skewed versions of student T would be possible. It would be interesting to look at.
Okay, thank you very much. Ikboljon, yana bitta savol bor edi, agar vaqt bo'lsa agar.
Yes, yes. دايما on econometrics.
Okay, Rustam, okay, the last, I really want to know about this predictive regression. Okay, so now that let's say that we're applying this predictive regression, okay, in terms of the financial data. Okay, so the YT is a function of the XT. XT is a different variable. The XT is equals to rho XT minus 1 plus a return. Okay, in the financial data come back to the same point again. So it's a heavy tail. So now that we're testing this crypto, the heavy tails in the crypto, as you can see, the sum of the times that even the variance is not finite, right? It's infinite. So meaning that it's very heavy tailed. So in the context of heavy tails, applicability of this predictive regressions, what do you think about this under the condition of the heavy tails, the predictive regression?
Yeah, so here, thank you, Akram. It's very important. We have the problem of outliers, and that affects the distribution. As we know, in the case of sample means, say, that will not converge to normal if variances are infinite, right? We will have convergence to stables. What is important about these methods, they work if convergence of group estimators is to scale mixtures of normals. Scale mixtures mean convergence is to symmetric stables. That actually relates to your question, Akram, on asymmetry. Say, sample mean will converge to scale mixture to symmetric stable if we have enough symmetry in the initial observation. Will be asymmetric stable if there's a lot of asymmetry. So then, if it's asymmetric heavy tails, then one should think what to do, like symmetrize the data perhaps. But importantly, the heavy-tailed case of observations is also covered in many settings by the approaches. Also, what can we use under heavy tails? It's only subsampling or bootstrap, right? But this approach is much simpler to implement than subsampling, and bootstrap has better finite sample performance than subsampling. It's discussed in this our book with my father, Marat Ibragimov, and John Walden. Concerning heavy tails, if I may take 1 minute, I would like to mention of ongoing research with colleagues, also the topic that we discuss with Akram, it's on the analysis of what is responsible for crisis. We know, as Akram mentioned, returns are heavy tail. This is the case for many other variables also. But what are actual reasons why we observe large downfalls in stock market? One may estimate the characteristics of heavy tailedness like Pareto exponent for each of the stocks. We did that for different Russian stock companies. And then for each return we get tail index. We can regress that on, by the way, it's smaller than 2, maybe smaller than 2. Variances may be infinite. Force moments are definitely infinite here. We can regress that on different characteristics of the companies. This is from our published paper. But I should confess that the standard errors here, they actually are not the statistically justified ones. Indeed, in the first stage, we estimate tail index And then in the second stage, we regress estimate on the characteristics of the company. So there's uncertainty in the first stage. So, but still, it's two-stage procedure. Usually one considers this tail regressions, but in principle, and importantly, one can use the statistic approaches, run these regressions for groups of observations, and then base the inference on the statistic approaches. It would be great to consider this in the analysis, perhaps for green stocks also. This was the topic of our research with Akram. Thank you very much.
Yeah, thank you very much. Thank you so much.
Thank you very much, Akram, and thank you very much, for extensive response to the questions. Any questions from the audience, please? You're welcome to ask. In the meantime, Rustam, I would like to ask you to elaborate on some of the key differences between, just simply elaborate on some of the key differences between the traditional t-statistic and robust t-statistics for financial data analysis.
Just 1 minute. Let me, perhaps it should be somewhere in the slides. Just 1 minute. Thank you very much for the question.
You're very welcome. And to our audience, if you have any difficulties asking questions in English, please do not hesitate. You can write it in the chat box, or you can actually ask the questions in Uzbek or in Russian language as well.
I must have it. Let me just open the slide. It's just
yeah, sure, no problem.
If it's okay.
Of course.
So, as we know, in fact, inference, we divide the estimator on the estimate of its limiting variance. Say, in OLS regression, we account for potential autocorrelation in our variables. In regression, I'm opening the slides right now. It's autocorrelation of u times x, or the error of the regression multiplied by the regressor. Naturally, in the case of autocorrelation, the variance of OLS estimator is not just sum of variances of each summand. I think now I can share the slides here. Yeah, right now. It can be seen, right?
Yes.
My slides?
Yeah, it's
can be
visible.
Okay, thank you. So naturally, suppose that it's about testing whether the mean of certain time series equal to 0. So what do? We just look into the sample mean of my observations. But suppose that our observations are correlated over time. So we will have, for autocorrelated time series, the average of our observations being asymptotically normal. But the limiting variance is different from variance of each observation, as in the case of IID. Or put it differently, in the case of OLS regression, we now it's about Haq standard errors, right, Felix? My slides.
Yeah.
Yes.
Yeah. Okay. So in the case when X and U are correlated over time, variance of OLS estimator involves sum of variances and plus different covariances. IID standard errors is about variance of this U, V divided by variance of X. But Haq or full sample t-statistic is about accounting for all covariances. Haq is just estimating all autocorrelations, then looking into estimate of standard error that accounts for these autocorrelations. It works well in theory. Indeed, we have consistency, but as we discussed, doesn't work well in finite sample. T-statistic in large samples is standard normal, but large samples, a lot of data, tens of thousands of daily return observations are needed for this to hold. On the other hand, in finite samples, we have poor performance. And then our methods are about simple approach. Now, their t-statistic was about OLS estimator. It's another set of slides, right? Robust inference methods. Yes?
Yes.
Our method is about the alternative approach. Estimate the regression for groups, and then in the second stage, for these Q group estimators, we look into the t-statistic. Full sample t-statistic, Haq t-statistic is about full sample OLS estimator divided by this complicated expression. Our t-statistic is about t-statistic calculated for two group estimates, or maybe Q. Thank you very much. Okay,
Thank you very much,
now,
Dr. Ibragimov. And we have another question from Yevgeny, I believe.
Yeah, thank you very much.
Okay.
Yeah. So can you hear me well?
Yeah.
Yeah, thank you very much for the presentation. I have one question. Did you consider the application of your estimator in the context of seasonal data? For example, if you have daily data and it has multiple seasonal patterns, whether this estimator works?
Thank you very much. Seasonal means we will have dependence, say, of today's data on a year ago, or cyclical type of dependence.
Rustam, okay, can I take this question?
Yeah, thank you. I will show some slides related to this.
That's fine.
Yeah, please, Akram.
Yeah.
If you...
Okay, so Evgeny Solberg, right?
شنو أكرم يبغى يسوي
Yeah, I'm here.
Okay. Look, so this is a financial data, and you don't have this, seasonality in the financial data. It's just a stochastic process. Realizations of financial data is just realizations coming from some random walk process. Okay, we don't have any seasonality here. So in the financial
but
data,
we can think about, say, economic growth, right? And other types. Yeah.
In
Let
this
me
case, it
Yeah, for
let
the
me
quarterly, right, Rustam again? If there is the GDP, is the quarterly.
yeah. Let me show something, and it relates to important question. Thank you very much. On applicability of the approaches, statistic approaches. It's important that in applications of OLS, of the statistic approaches, it's important that our group estimators are asymptotically normal and asymptotically independent. So essentially, we need to be sure that these group estimators are just Q independent observations with possibly different variants, and then we use the small sample result to obtain justification. The question is how to form the groups in order for these conditions to be satisfied. For instance, suppose that it's some type of dependence, maybe seasonal. GDP today in this quarter depends on its value for quarters before. GDP in the next quarter depends similarly on GDP for quarters before and so forth. It's okay to use the statistic approach, but the groups should be formed in such a way that the assumptions of asymptotic normality, these slides are seen, right, colleagues, or maybe not.
Yes, we can see the slides.
Let me be sure that they are seen. I'm back to these slides, and the assumptions for asymptotic validity of the statistic approaches. It's asymptotic normality for group estimators, asymptotic independence. But what is there for asymptotic normality? Center is the same. Suppose groups are formed that in one of the groups I only put GDP in the fourth quarter. In the second group, I only put GDP in the second quarter of each year and so forth. Naturally, we will have differences in the mean of GDP in the first group, in the second group, and so forth. If the groups are mixed, or we somehow randomize the GDP, seasonal GDP, and then form the groups as in time series, then it will work. It's kind of similar in inference on income inequality. Suppose that I estimate income inequality in a certain country. Let it be, say, Russia, for instance. Groups. We have Росстат conducts household surveys on the income and other variables. Now it reports the results of those surveys. We can form the groups by looking into the regions, but what happens if we estimate income inequality using that data for Moscow? We will estimate the inequality for Moscow, but not for the whole country. We need to look into the data without any markers like into time series, kind of mix them, and then form the groups as in time series. I suppose it's the same under seasonal dependence. It would be great to consider this actually, how groups should be formed for the approaches to be applicable. Thank you very much.
Thank you.
Thank you very much.
There were some questions in chat.
There was a question about some econometric techniques that you could suggest for analyzing the impact of digitalization on green total factor productivity. But this is a little off topic, but
it's interesting. Indeed, there are there are, as we know now, variables related to digitalization, AI, they enter all our life. I should mention, say, a paper that is currently a hit in finance. Perhaps you may know it. It's about predictive regressions and whether ChatGPT can predict asset returns. It's I'm trying to find it. Stock prices. It's still a working paper, apparently because of a good reason. One needs to look into statistical analysis and see that there is not much on statistical analysis actually here, but it is the first paper that just that was published on the web, and with the claim that ChatGPT sentiment can forecast future stock price movements. We can use ChatGPT for many things, right? And interestingly, sentiment over certain financial news can be extracted. Feed a financial news into ChatGPT and ask, what is the sentiment on the scale from -1 to 1? -1 is negative, 1 is positive. It will give a number. And then, according to this paper and many other researchers I talked about, or you may have talked about, that sentiment number predicts future asset return. So there's not much on econometrics and on application of correct standard errors, as I understand, and it would be interesting to look into robust inference. Similarly, for other variables like index of digitalization, important variable for many key variables, including economic growth, others. So one can include that in predictive regressions for different variables and indeed look into predictive ability using different methods. It would be interesting to consider its time series property and motivated by that, possibly use robust inference methods as well.
Thank you, Professor Ibragimov. There's another question in chat. Dr. Hayat Sadalif is asking if whether it would be possible, or you can elaborate on the topic that integrating machine learning with structural economic models to improve the efficiency and accuracy of predicting financial markets.
Thank you very much. It's the question many colleagues and students in economics and finance think about. Without direct comparison means without comparing predictive ability. I think what is important for in machine learning applications, we have naturally different approaches, and including black box approaches can be used to construct a predictive model also that may be good in terms of some characteristics like R square, but R square it's widely used, but apparently not the best way to compare performance of predictive models. Now there are well-defined tests. It would be interesting, and I actually encourage our young colleagues and students who deal with machine learning. In master thesis, students find a lot of, or developed a lot of machine learning predictive models, compare them with well-justified predictive regressions, perhaps involving dividend price ratio. After all, this regression is well justified in theory. We know in order to price stocks, we need to look into net present value of future dividends. There is a reason why this model or earnings to price ratio work, perhaps not so much for different machine learning methods, but it would be great to just to approach the analysis comparison thematically and see whether indeed there are crucial advantages in going from simple model to complicated machine learning. I hope this answers the question to some
Thank you very much,
extent.
Dr. Ibragimov. There's another question from myself. I've seen that you have shared a presentation regarding crypto market. I think you had a presentation about Bitcoin. How effective would be econometric? How effectively can we use econometric models to model the change in cryptocurrency markets? Whether it would be possible to predict the market, because the crypto market is full of irregularities. Sometimes, as you know, one tweet by some of the influencers in the world, some of the global influencers, would cause a market growth or market destruction for any cryptocurrency.
Thank you very much. It's very important. And indeed, when we look into emerging markets or new markets, including cryptocurrencies, a lot of things are unknown. The markets are much, well, unknown how to price them, of course, or whether there indeed bubbles in the market. Not much on forecasting returns, volatility. There was important research on predictive models for cryptocurrencies. Leo and Savinsky, had important papers in 21 on predictive models for Bitcoin returns and cryptocurrency returns. They looked into, say, momentum regressions. RT regressed on past return, do not find well, interestingly, IID standard errors, they should not be used, but they indicate significance. We talked with Leo and Savinsky, and they, in the published version, they use Hack standard errors as it should be. Hack indicates some significance. We looked into statistic robust inference approaches. Naturally, well, they are more robust. Some statistical significance in Hack disappears. By the way, it's not the case for predictive models that we talked about. No predictive ability of dividend over price we saw in Campbell and Thompson, but statistic approaches indicate significance. So the conclusions may be vice versa, like we obtain significance for some of the factors, like momentum factor in Fama-French regressions, where Hack standard errors do not indicate significance. Leo and Savinsky paper is very important paper because it considers price to dividend ratio as a predictor for cryptocurrency returns. We can, my slides are seen, right, colleagues?
Yeah, we can see the slides.
Crypto. So it considers price to dividend ratio for Bitcoin, but crypto doesn't pay dividends. But what is then dividend? Why do people buy crypto? Because they have some usefulness. Maybe avoiding transaction cost, maybe being able some goods, including illegal ones, as we know, that are not available on the standard markets, they are useful. And then that usefulness is has a predictive ability. But if it has predictive ability, then it should be priced. So we can think about pricing models for crypto that would include not dividends. By the way, sentiment is also, well, maybe important, but that usefulness should be priced. And we looked into some pricing models that involve standard, well-defined measures of usefulness of crypto. Also apply that in new test of bubbles. Bubbles is about whether price of crypto is greater than fundamental value price that comes from pricing equations. That paper is available, and we would be grateful for comments. So they are great nature, crypto, other new markets, emerging markets, are natural applications of robust inference because markets are much more volatile than developed ones. And much less is known for them. Actually, it would be great to use ChatGPT sentiment in inference on predictability for Russian market, other emerging markets. Also, look into new markets and important markets like green stocks, where properties of the markets are different from developed ones. Thank you very much.
Thank you very much, Professor Ibragimov, for your time and for the presentation. Dear audience, if you have any questions, please do let us know. And if you don't, we're going to wrap up our webinar session today. And we look forward to hosting Professor Ibragimov here at the Graduate School of Business and Entrepreneurship physically when he's in Tashkent. So we look forward to meeting you in person. Thank you very much for your time, and thank you very much for everyone tuning in. And we look forward to hosting again seeing you again in the next series of the Research Talks webinar. Thank you very much, everyone. Rustam, thank you very much for your time.
Thank you
very much, Ikboljon. Thank you very much, colleagues. Great questions and discussions. I also look to being in Tashkent in person and also to discussing research in person. My contacts are available, and I would be grateful for email discussions as well.
Absolutely. Kasimov, thank you very much as well. Yeah, with key questions you participated in today's presentation. Thank you so much. And Dr. Hayat Saidali, thank you for making this event happen. And would like to thank Piradin Alayarov as well for helping us organize this event. Thank you so much, everyone.
Thanks a lot.
Thank you.
Rahmat. Rahmat.